Tell me when. Got it.
Wait, what's that sound? No, esto ya lo prendiste.
Sí. Hello, folks. Another day, another lecture. And yesterday, when we adjourned, some questions remained, especially about motion. And I covered the history of motion, and after that, some issues remain. And one of them was the scientific definition of motion, especially the one that I propose, and my son Adrian, who's on the other side of the table here.
Hi guys.
He questioned it, and we had a good fight over it. I won, as always. I'm going to talk about also the question of whether motion is continuous. And I want to raise another issue, which is that definitions have to be comprehensive. In fact, they are for the purposes of the rope hypothesis. We build this foundation, and all these definitions are interrelated. So let me go on with the history. Let me do a summary again of a synthesis of what I said yesterday. Essentially, I'm saying that the debate over motion, I think, started with Plato. Now, he wrote it down, but I'm sure it started even before with Socrates. But that's around the time when it started. 4th century BC, that's a good time frame for when they started debating the word motion in a, you can call it scientific or philosophical matter, when they realized it was an important word. And the problem again is that both Plato and the guy who comes after him, who is his student, Aristotle, they wrote about it, but neither one really defined the terms. The term motion. What they did was they used synonyms. Okay, they used the word change, alteration, words of that nature, and Plato was a little more using his intention was to use the word more in terms of what the soul does. He wanted to show that the origin of motion starts with the soul. The soul is what penetrates the body, and the body is essentially a statue until the soul penetrates it and gets it moving. Aristotle comes later and he says, no, look, there was an unmoved mover. He's the original guy. I guess we're talking about God here. And what he's saying essentially is that, there was this chain reaction, these dominoes, and there was a first domino which was unmoved or could not move itself, okay? And apparently after that, it started moving and began the rolling of the dominoes. So anyway, you want to interpret that. the point here is that neither one defined the word motion in a scientific manner. That's the first issue. And we go through many centuries, and nobody really touches the word. They just rely on what both Aristotle and Plato said, until we get to the 13th century, and we have St. Thomas Aquinas. And what Thomas does is he takes Aristotle's view, essentially. And he says, and the reason he takes that view is he wants to prove the existence of God. His first proof has to do with motion, and has to do with the argument presented by Aristotle that there is a first unmoved mover. And so essentially that's where that goes. It's not very scientific. Again, he doesn't have a definition. He just uses what Aristotle had. And so there are no definitions up to that point. Now we come to the 17th century. We get to Newton, Isaac Newton, and there were a couple people in between there that touched the word motion. But as far as like a major discussion on motion, I guess you could say Newton, because he came up with the 3 laws of motion. But again, Newton does not define the word motion. Okay, in fact, he says, specifically in his scholium to the Principia, he says, I do not define la 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 and motion because we already know what they mean. Okay, so he has no definition. And after that, we get to really Einstein is probably the next guy. He deals with it at the beginning of the 20th century. And he talks about, he's got this paper, it's called On the Electrodynamics of Moving Bodies. Moving bodies, you would think he was going to talk about motion. And he does talk about motion, but not from the motion point of view. He doesn't define motion. He talks about it from the time point of view. He introduces time. And we get to today, and we don't have a definition. If you look it up in the dictionary, what you're going to find is a synonym, the word change specifically. So motion has changed, and change is motion. We haven't learned anything. And that's the status today. Okay? So what have I done? I've introduced a definition, which I maintain is scientific because it can be used consistently, and it does not rely on synonyms. And we do need to define the word motion for the purposes of physics. We can't avoid the subject. And so it's part of the lexicon or the grammar words that we absolutely need to do physics. And before that, you have 3 other words, and I'm going to put them up here. That's the scientific definition that I presented yesterday. It consists of at least 4 definitions. We have the word object. We have the word distance, location, and only after that can we get to the word motion. The first 3 of these are static concepts. There is no motion involved, for example, in distance. We're not talking about unrolling a measuring tape. We're not talking about counting seconds on a clock. What we're doing is saying that, distance simply is separation between objects. And objects is that which has shape. And then location is the set of distances from every object in the universe, every atom, whatever level you want to deal with, to the test object. Now we get to the first dynamic concept, and that's the word motion. We define it as 2 or more locations. Okay? And that's the status now. Now, what is the issue with these words? The issue is that, is this a scientific definition? And my son said he doesn't agree, or maybe he's got a better definition. I don't know what his argument will be here. But he says that we have a problem because time is involved in my definition. And I try to separate those 2, and I'm saying the following. For time, you need memory. You need either a living entity or a recorder, a videotape recorder, to show that this object was over here, and now it's over here. Okay? You need that memory. You need to show 2 locations for time, but you need to compare one set of motions against another. In other words, time is a comparison of 2 motions. Motions of 2 objects.
Not one set of motions.
Two motion. In other words, motions of 2 objects. And you need to have 2 objects to do time. You need to compare them, and you need memory. Okay, that's for time. What I'm saying is motion doesn't require that. Motion is just a definition. If an object, by definition, if I'm going to give a presentation, I'm saying somebody asks me, what is motion? I'm going to say two or more locations. And that's by definition. As you can see in the definition of motion, there is no requirement for an observer. If an object by itself, no humans, no life existing in the universe, if an object has two or more locations, we say that it moved by definition. That's what I'm saying with that definition. I'm saying that if we're going to use this consistently, we got to say, well, did the moon move? Well, did the observer see it move? No, that's not the issue. The issue is, did the moon occupy two or more locations? If it did, we call that motion. We refer to that phenomenon as motion. That's what I'm saying. Conversely, time, you need to have two things move and compare them. So you need memory now. You need someone to make a relation between this motion, and I'll give an example. For example, the motion of the Earth around the sun against the motion of the seconds on my clock or on my watch, or the minutes or the hours or whatever. And what am I saying here? I'm saying that the Earth moved 30 kilometers when my second moved 1 second. In other words, went from one stick to the other. So I'm comparing the motion of the Earth against the motion of my watch. We're doing a comparison. That's what I'm saying is time. Time is a comparison of two motions. Okay? And again, you need memory.
In the definitions.
Well, I don't put time in there because we don't need time in physics or in science. That's why I don't put time. Time is not a crucial word. We don't need time. Okay, and that's why I never include it. I just criticize it, and I'm saying this is what the mathematicians are saying when they say time. So I'm putting words in their mouth because they don't put them in their mouth. They can't tell you what time is. So I'm saying this is what you're saying it is. Okay, that's what time is, and that's what everybody understands by time. Because people get these weird definitions. Time is what a clock measures, or we don't know what time is, or they get all these kinds of answers, and all those answers are unscientific. The scientific definition of time, of what they're referring to when they say time, is, look, when the Earth moved 30 kilometers, my second hand on my clock moved 1 second. And you multiply that times 5, you move 5 seconds, the Earth moved 150 kilometers. That's what we're saying. We're comparing two motions. And you can do that with almost anything. You can say, well, the dog ran, it took 5 seconds. You're comparing how much time the dog went from A to B, and how much time your second or your minute or your hour on your clock went from one place to another.
So when you say an action happened after another.
Okay.
So B happens after A.
Yeah. Now
are you invoking time when you say that?
Yes, you are, but you're invoking a different kind of time, and I've got that in my book.
Kind of time.
No, let me specify. One is qualitative time, the other one is quantitative time. When we say before and after, yesterday and today, we're not really referring to a clock or to any measurement. We're just saying this came before that, And then we're talking about qualitative time. Only qualitative, in a qualitative sense. We're not invoking seconds or minutes or hours. But when we invoke seconds, minutes, or hours, now we're getting the measuring tape, right? We're using pre-established units. We're bringing that into the discussion, and that's a little different than talking about qualitative time. But
quantitative time, you're saying, is the relationship between two objects, but qualitative time is something else?
Qualitative time is also the relationship between two objects, but in the case of one, like when you're talking about seconds, minutes, hours, a quantitative time, now you've got some pre-established units, because I'm sure if we go to another planet and they have a different year, a different minute, a different second, maybe they have a different measure of time, because we have agreed here on Earth on what is a second, but maybe in another planet they have a different second. Maybe their second is a second and a half. For all we know, right? I mean, I'm sure if we go and live in Mars, right, their second's going to be a little different than ours because they take longer to make the year. And the year, the second was established originally based on the year, Okay.
It's a fraction of the year.
Yeah, it's a fraction of the year. I think it's 38,400 or something like that. I can't remember the exact number. I think, and I don't know if that's the hours or the minutes or the seconds. But the point here is that, no, it can't be the seconds. That's got to be in the millions. But the point here is that, if you go to a different planet, it's going to have different time. And you have a different civilization, they'll have different time. And in fact, we had different time when we had the original people, the Indians, like the Aztecs and so on. They used a different calendar. They used. I'm sure their calendar did not match the Roman calendar or the Christian calendar, and we're talking about calendars here. But still, that's time. That's a measure of time. But the point here is that those are pre-established units. First, you got to establish the unit and say, I'm going to talk about the second. You measure and you say this is going to be a second. And now you're going to use that to qualify time in a quantitative manner. Whereas when you talk about before and after, you're just talking about qualitative time. But in both cases, you're talking about the comparison of two motions. What is before and after? You have to compare the motion of one guy to the motion of another.
Do you? What if nothing moved?
Then you don't have time. You have, first of all, everything moves in the universe, but you're saying nothing moved. That means we froze the universe. I would think there's no time. I guess that's where the Big Bang started. Nothing moved.
Yeah, the question is, how can you talk about motion without invoking frames or time?
Yeah, okay, and again, we have to put in the right context. We're talking about a scientific definition here. And all I'm saying is that when I pronounce the word motion, and I say the moon moved, or the dog moved, or the rock moved, whenever I say that, all I'm saying is that thing occupied two or more locations. That's what I'm going to, that's my definition, that's how I'm going to use the definition. So I don't need to say, well, did I see the dog move? Did I see the rock move? No, I'm saying if the rock occupies two or more locations, we're going to call that motion. That's the way we got interpreted. In the case of time, we can't do that. In the case of time, you absolutely need to observe, have memory, or to record a recorder, some video or whatever, and it's got to compare two motions. And only then can you have that relationship that we call time.
But when you say motion is an object occupying two or more locations, you're invoking frames.
Okay, and that's another thing that's the next issue. Let me clarify that before you get into the question, because maybe I'll answer your question with what I'm going to answer now. And that's the issue of continuous. Is motion continuous? And according to my definitions, we got a problem, because you're saying, well, hold it. If you see the definition there on the screen, it says location, right? And distances from all objects to the target. And motion is two or more locations. But if location is a static concept and motion is the first dynamic concept, we got a little bit of a contradiction there, or a seeming contradiction. It appears that there's a contradiction. Location is kind of like discrete in our minds. We're saying, well, location, it's a static position of an object. This is the location at cross section of time
like
in the universe.
One frame of the universe,
right?
Just to see what the distance between everything is, but
right.
It's actually in motion.
Right. So we got a cross section of time in the universe, or one frame in the universe. And so now we have one frame. And now we say, well, motion is two or more frames. That's what we're apparently saying, right? And so you say, well, okay, if I look at a movie, right, and I see one frame and another frame and another frame, it's discrete. We have all these discrete locations. We run the tape, and now we have motion. But, at the nitty gritty, it looks like, we have all these chopped up locations forming motion.
That's why they call it moving pictures, because they're pictures.
Right, moving picture, motion pictures, right? But no, let me clarify that. There's two ways of looking at this, what motion is and what a motion picture is. Here we have a frame, here we have another frame, here we have another one. That's the way we always seen the films, right? But now, what if we see them lengthwise instead of sideways, right? We see them lengthwise, and they're stuck together one to the other. So we have a book, all the pages of the book, right, one right next to another. That's how we should see location. Location, you can't chop location in half, right? And you can't chop one of these frames of the universe in half like sideways, like one frame from another, and you cut it there, you splice it. No, here we're talking about continuous locations, okay? And they're all stuck to each other because it's not like the object stops at this location and then says, okay, 2 minutes later,
take a picture.
Yeah, then goes to the next frame. That's how we do the film. But that's not what happens out there in physics, in the real world. In the real world, it's a continuous locations. So they're all touching each other. And the best way to look at this is not sideways as frames in a film. You got to look at them as the pages of a book. They're all one right next to another. They're all touching neck to neck. And no matter where you cut that motion, you're going to find a location. That's how we got to look at it.
I like that way of looking at
okay,
it. It makes it easier to think of instead of discrete frames. It kind of does make more sense when you put them all together because that's how something moves.
Yeah.
In the real universe.
But let me clarify one more thing, which is very, very important. Keep this in mind, and this is important, okay? The word continuous in physics is an adjective. It cannot be used in the context of motion or location, which are concepts.
Wait, say that again?
Yeah, continuous is an adjective. Discrete and continuous only can be used to qualify objects. You can say the table is continuous, or better still, a cube. An ideal cube is not thought of as made of little pieces, no, it's continuous. It's made of a single piece. An ideal cube is perfect. It has no holes in it. So from a conceptual point of view, a cube is continuous. A circle is continuous. Okay? So that's continuous. That's where you can use the word continuous. You cannot say that information is continuous.
Well, you're redefining the words.
Yeah, keep in mind that we have a new language here, and it's important to understand this language. Adjectives that are words that are adjectives in ordinary speech cannot be transferred without any scrutiny into physics. In physics, if the word motion in ordinary speech, the word motion is a noun. In physics, it's a verb. Orbit is a noun in ordinary speech. In science, in physics, it's a verb. Orbit is what something does, not what something is. Even though you say, well, I can talk about orbit. That's in ordinary speech. You can't talk about orbit in science. You cannot say, and I always use this example, you cannot say the orbit of Jupiter. I'm going to talk today about the orbit of Jupiter. That's a wrong language. You got to say Jupiter orbits. Orbit is a verb, comes after the noun. Jupiter's the noun. That's the way we have to do it in physics.
What about the path of Jupiter?
Again, if you're talking about the itinerary or the highway.
What do you mean?
Well, I mean, for example, we're talking about the yellow brick road, or are we talking about the itinerary along the yellow brick road? So if we're talking about motion, the itinerary, the trajectory, that's a concept. That's motion. But if you're talking about the road, again, if you're talking about the road, you're talking about the noun. But if you're talking about the itinerary, it's not a noun; it's a verb.
So
the word itinerary in physics is a verb.
How would you rephrase the orbit of Jupiter?
Jupiter orbits.
We're going to calculate the orbit of Jupiter.
We don't calculate, first of all, but again, you're talking about.
Just rephrase the sentence.
You can use that sentence in science. You can say it. The point that I'm trying to make is that whenever you say that, you have to be aware that the word orbit at all times, no matter how you use it in physics, is a verb. So you can say the orbit of Jupiter, but at that point you're not really talking about a noun, even though it's the subject of the sentence. Yeah. All you're saying is, I'm going to talk about the itinerary of Jupiter. I'm going to call that the orbit or the motion or whatever you want to use in there. But you're talking about the verb, the action. You're not talking about, look, I've got an orbit in my hand.
Does field fall under the same scrutiny?
And we have the same problem with the word field. Field is a concept, again, and it's a dynamic concept, which people don't understand that, but it's a dynamic concept.
But the threads are fielding.
Yeah, the threads are moving, and the moving threads, that's what we call the field. okay, and so on.
Well, we get back to
Okay, but
continuous.
the point here is that the word continuous is an adjective. It can only be used to say the table is continuous or a cube is continuous. The correct word is incessant. Motion is incessant, not continuous.
You mean can be incessant?
Yeah, okay. Well, it is, in fact, in the universe, it is incessant motion. But you're right. It can be and it is in our case. But my point is, that's the correct word to use. And incessant, in ordinary speech, what is it? It's an adjective. We can't use it as an adjective in physics. In physics, it's an adverb. Why? Because adverbs qualify verbs and adjectives qualify nouns. You can say the table is red. So now the table, what does that mean? Now, you're using the word red as an adjective, and that's correct. You can't say motion is red or the itinerary is red, okay? You can't use that kind of language, in physics at least. You can do it in poetry maybe, but not in physics. And in physics, similarly, you can't say, the table is continuous. But you can say motion is incessant, eternal, perpetual. You can say all that, but you cannot say motion is red or continuous or straight.
You can say the table is continuous.
Right, and you can say motion is rectilinear or curvilinear. You cannot say the motion is straight. No, that's the wrong word. Straight is what an arrow is. Straight is what the table is. You can say that, but you cannot say, or the edge of a cube. But you cannot say that motion is straight. So we have a new language, and be aware
that have to be applied to verbs that are similar, but it's like you're taking one concept and giving a word, splitting every concept in two. One applies to motion, itineraries, and the other part of the concept, the other word, applies to objects. It makes it much more straightforward.
Yeah, it's a black and white issue. That's the point. If you're going to use adjectives, only apply to objects. What is an object? That which has shape. You can say that the table is red. You can say the table is continuous. You can use it in that sense. Likewise, if you're referring to something that has motion, to some dynamic concept like information is a dynamic concept, I think, right? Because it's like a flow of information, I guess. Maybe you can even say that
book, but it's really how you use the book.
Well, again, you have to know what you're referring to. If you're referring to orbit, it's under all circumstances the word orbit is a verb. Now they've turned orbit into orbital. The orbital, the energy levels, the orbital of an atom, and they've turned this verb into a noun. They turn infinite, which is an adjective, the infinite table, and they turn it into infinity, into a noun. And they do all these magical things in mathematics. Those are prohibited in physics. There is no such thing as infinity.
Why do you draw this stark line between motion and static concepts or static objects?
Crispiness. I like things crispy. I like my cereals crispy. That's why. It's crispiness.
It's precise.
It's precise. It's precise. It's black and white. There's no ambiguity. But if you say, well, the orbit, it turned into the orbital, and the orbital, then you're messed up, because now you can't follow the dissertation.
Is it because you can then say things like the motion is red or something like that?
It's worse than that. What is a black hole? I mean, we don't have a definition for the term black hole. And when you look at the definitions, there's two irreconcilable concepts or definitions. One is as a black ball. This big star condenses, and it shrinks to what? And this is from the NASA site, okay? No. In fact, it doesn't. No. If you go to the NASA site, you'll find several of these. There's not only one. There's like 3 or 4 notions of this. It says to the size of New York City.
The black hole.
The black hole. So this big star, right? It lost all its stuff. It condensed. It shrunk. It compressed all the matter, but it doesn't disappear into a singularity as we always thought. If you go to the NASA site, you'll find this. Don't take my word for it. It shrinks to a ball, the black ball. This is the 8 ball or a bowling ball, the black bowling ball, the size of a New York City. So they're talking about an object. And then when you look up the definition, or you see other sites, they'll say that the black hole is a region of space-time. So here we have a star that shrinks so much that it becomes a region of something else. So we have a problem because they don't have a definition for black hole. Is the black hole, an object, a standalone object like a ball? Does it shrink to a ball and it's this ball that has so much mass? Or does it shrink so much that it turns into nothing, singularity, point nothing, because it has no size, no volume, and it's part of space-time? It's a hole that takes you to another universe. Turns into Bugs Bunny's hole in the ground. We're not talking about the Earth. We're talking about the hole inside the Earth. So is the black hole a standalone black ball, or is it a hole? Is it Bugs Bunny's hole? And again, that's the problem we have, and that's because of language. That's all language. That's the when they say that space-time is an object. Stephen Hawking says this in A Brief History of Time. It's a four-dimensional object, and don't try to imagine it. Hold it, what do you mean an object? I mean, you might have doubts about space. You might say, well, I think space is material. But surely time is not an object. Time is a concept. And if I take a concept plus a tree, it doesn't make a four-dimensional tree. Okay? I have a three-dimensional rock plus love. I don't get a four-dimensional object because of that. Okay, and this is the issue. The issue is that these people are blending concepts with objects, and they get away with this because of language. It's all language.
Well, before we got into the language, we were talking about how can you, when you say motion is an object having two or more locations.
Uh-huh.
When you say an object is motion is an object having two or more locations, that you're implicitly invoking frames or memory or time.
Uh-huh. And what's the question?
That you're evoking time when you're talking about motion with different frames.
Yeah, and what I'm saying again, time should be separate from motion. And they're not the same because time involves two motions. Okay? Time requires a comparison of two motions, two distinct motions.
Now, what do you call frames?
Well, when I use the word frame, I use it only in the context of the universal movie. I'm saying that if we take cross sections of time, right? You take just a cross section of this continuous universal movie, and you have to think of it not side by side, all these frames, but again, like stuck together like pages on a book, then it's continuous, but we separate, like we can chop time or the motion of all the locations in the universe. We can chop it at one point in time, say we froze the universe at that point in time, and now we have distance. All we have is distance to the test object. That's all we have.
That's where the problem comes. It's like when we were talking about the rope or the thread, when you're saying distances between the rope or the thread, you have to take a chunk of this continuous object. You're essentially, when you're talking about two or more locations, you're taking chunks from this continuous movie.
Correct.
So you can't really take a chunk out of a movie.
Right,
that's where the problem with the definition of motion comes.
It's tricky, but again, I keep bringing you back to square one, and the square one is the following: we're going to use the word motion consistently in physics, and what do we mean by that? We mean that when I say something moved, the rock moved, I'm saying the rock occupied two or more locations. Does it mean that I saw it? Does it mean that I filmed it? Does it mean I recorded it? No. It just means that if we take all observers out of the universe, if we could do that, if we kill all the observers, like I always say, it's like the mafia, you kill all the witnesses. The rock moves. When I say the rock moved, I mean that the rock occupied two or more locations. And we don't need an observer for that. The rock moves by definition because that's what the word motion means in that context.
I think the part where someone could get confused here, including myself, is anytime you're talking about the past, you're invoking memory, because there is no such thing as the past. So but you're saying it had two or more locations. You're saying you're putting someone in the movie. By definition, you're summoning a witness when you're saying two or more locations.
Yeah, but that's the point that I'm trying to make here is that it's not. It's not, and primarily because we're not saying that we need to have an observer that saw the rock move, or that measured, or that filmed or recorded in some way that the rock occupied two or more locations. We're saying in the absolute, the moon was moving before any humans were born on Earth. What do we mean when we say the moon was moving? We have to define that situation when there's no observers, because there were no observers millions of years ago, or at least of a few billion years ago at least. There were no observers here on Earth. There was no life. We take it before life began on Earth. Was the moon moving? Yeah, the moon was moving. What do we mean by that? We mean that it occupied 2 or more locations. Was there time? Well, there was no one to make the comparison. So there was no time, but we had motion.
But when you invoke the past, you implicitly invoke a watcher, because you need memory.
But we're not invoking
This is my point. The past only exists in our minds.
What I'm saying is we're not invoking the past.
But when you bring up the past, when you say 2 or more locations, you brought up the past.
No, because we define the terms. You're bringing time, and we haven't even got to the word time. I'm still. Here, let me put the definition once more because it's important here. Let me put the definitions up again. These are the only 4 words. I never got beyond these 4 words because I never was able to get to exist or to time or to anything else. Right? Straight. Any of the other words that we use in physics. I only got this far. Can I, with these 4 words, talk about the motion of the moon? And I can tell you that I can. I haven't defined any other words. Those are the only 4 in the entire dictionary as of this moment, right? There are no other words except the ones I used in between. So these are the only key words that I've got in there, okay? So if these are the only 4 words, can I talk about the motion of the moon? And I can safely say that I can, because I'm saying the moon is an object. It has shape. There is distance between, the moon and the Earth, okay? And the moon has location because there is a separation between the Earth and the moon and other objects in the universe. And I can say, did the moon occupy 2 or more locations? I'm saying I don't know if it did, because that would be an observer. That would invoke the past. But if the moon occupies 2 or more locations, I'm going to refer to that as motion. That's what I'm saying.
That's my question. How can an object occupy 2 locations? That's an irrational thought.
No, it's not. 2 or more locations, because that's all I'm saying. 2 or more locations.
How does an object occupy 2 or more locations? Let's just stick with 2.
I know.
How does a ball occupy? I've never seen a ball be in 2 places at once.
At once? What is this at once thing?
But that's what you're implying.
No, I'm not implying.
There's a lot more words in that definition than I think there are.
I'm not implying. You bring time in, and I haven't defined time.
2 locations. I've never seen a ball be 2 places at once.
At once?
Okay, I've never seen a ball be in 2 locations.
You haven't seen it? I can show you 2 locations. Look, here, let me show you. Watch carefully. Here's the ball over here. Now the ball is over here. Now, have you seen it?
I only see it there. Oh, my memory! In my memory, it used to be over there.
I'm saying that if an object occupies 2 or more locations, and obviously no 2 objects can occupy the same location as it does in quantum mechanics, okay? Quantum mechanics, they have 2 things. They have 2 objects can occupy the same location, okay? And an object can have 2 locations at once. That's how they explain the slit experiment, by the way. So they have these irrationalities. In normal science, in rational science, 2 objects cannot occupy the same location, and 1 object cannot be at 2 locations, okay, at once. But that's when we bring the word time in. But when we just say location, it says the distances from all objects to the target. If you're going to talk about 2 or more locations, obviously we're not talking about the same location.
Well, it could be the same location.
Yeah, but
if
then
everything stood still, yeah.
Yeah, but then you can't talk about 2 locations. You just one location.
One location twice.
Yeah, and or you're saying then yes, we have a frozen universe. So I think 2 locations is a good definition, but again, it's up to you folks to tear it to pieces. But that's my argument. My argument is, by definition, the moon moves by definition. And what is the definition? Whenever we say the moon moves, we're saying it occupied 2 or more locations. That's my argument. Okay, so now you know, when you see someone up there who criticizes you, that's my answer to that question. Okay.
Going back to the rope hypothesis now.
Yeah.
Can it be said that the rope has motion in the sense that because the rope
does move.
The rope moves.
It does move, but not in the way way we always thought that something like this moves. Keep in mind that an atom can move this way and that way and that way, but an atom is really sliding along the ropes like a bead on an abacus, right? A wire of an abacus, it just slides through there. It's something like that. But that doesn't mean that the ropes don't move. It's just that the rope doesn't move in the way, an atom moves. While one slides, the other one can move sideways, up and down, or like Mr. Plato said yesterday, the six motions, up and down, forward and backward, and side to side. Okay, that's what a rope can do. Can a rope twirl? I don't know.
Well, it's not exactly like a slide on an abacus.
Not exact, because what it is, it's remember when it slides like on an abacus, it's reconstructing itself in the direction of motion. That means the threads are coming and forming part of that part of the atom, and it's releasing thread behind. So it's like I don't even know if there's a analogy for that.
I don't think there is.
I'm trying to think of an analogy here, but this is the point. The point is, for any specific rope along which an atom slides, the threads are going into the atom. One goes through the center of the atom, the other one goes around it. And behind it, it releases that same thread. So it's moving along that thread like breaking into the rope. Okay, that's what it's doing. That's the idea. And then it can move sideways in the same direction along another rope and so on. But the ropes also can move because all the...
if you move an atom, the line goes with it.
Well, there's two ways of looking at this. And again, that's for smart people to see which one you think is more correct. You have two scenarios. One scenario is is my little ball here. Okay. One scenario is this. That one scenario is that the sun twirls the earth around along all these ropes, right? That's one scenario. Now here's another scenario. The earth encounters new ropes as it goes along, and the other ropes remain behind it. Okay? So that's another scenario, possible scenario.
Isn't it obviously the first one?
I would think so, because I think that's what's happening. I think the sun is twirling around, but remember something. Some of the atoms on Earth are constructed with ropes that come from very, very far away. And those ropes don't move as fast as the one within the solar system.
They don't move at all.
Right, and so we're crossing these ropes
that
that momentarily...
When you see something in the distance, it moves way slower. Like if you're on a train,
right.
Something close by goes fast, and something in the distance...
And my point here is that when the Earth comes around, let's say there's a bunch of ropes connecting the sun to the Andromeda galaxy, or to some star out there, right? Very far away. So those ropes, they move, but very slowly, versus the two objects which they unite, compared to what's happening within the solar system. The solar system, in comparison, is twirling around real fast. But what does that mean? It means that the Earth comes around, right, and goes through those ropes. And for a split second, for the moment it goes through that area, that rope forms part of your atoms. It's so weird. And then it continues, the rope remains behind, and only the ropes that are twirling you around the sun is what, primarily constitutes you. But remember, every time it goes in there, you have this rope, some of them go through you, and some of them are connected to you because they end in your atom. So you have both situations. You have a situation where you're going right through this coaxial. Let's call it a coaxial, right? And you're going through the coaxial. The rope that is connected to your atom, keeps going with you. But the rope that went through you and was connected to the atom in the sun, you pass through it. Momentarily, it maybe formed part of your atom. I don't know if it did. Maybe it does. Maybe it doesn't. I don't think it does. It just goes through. And you keep going through as the Earth twirls around the sun. So we have to look at that whole scenario, how it is in detail. Okay, it's a new physics, no doubt about it.
if magnetism, that's a different question for a different time.
For a different day.
And that was slightly more complicated. Let me ask this one.
Okay.
Do atoms resize when they move?
What do you mean resize?
Resize, change size, get
Well-
bigger, get smaller.
Well, obviously, atoms, they're all pumping constantly. Like I s-
I mean, when it moves.
well, again,
We
what I'm
were-
saying is, whenever an atom moves, every picosecond of the day, an atom is pumping torsion waves. Okay, so it's doing its quantum jump. It's boom, 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 boom at a great speed, and so it's constantly moving and it's constantly growing and getting small, and it's like a spontaneous. I mean, if Bohr's quantum jump is correct, all we're doing is seeing a little heart going boom, 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 just pumping torsion waves to other atoms. And so this motion is constant. So the atom is constantly getting bigger and smaller.
That's not what I'm talking about.
Then
I'm
what do
talking
you-
about when an atom changes location. Does it resize? An
I don't-
atom on
I
the
don't-
edge of the universe,
Uh-huh. Yeah.
coming towards the center of the universe, you could say.
Okay, yeah,
where
let's
there's
assume
most
that.
mass.
Let's assume there's such a thing.
If an atom is way out on the fringes and is coming towards everything, isn't it reeling in all the rope and essentially getting bigger? I mean, the pulse
No, because it's releasing rope behind. Remember?
behind where it's at the edge.
Well, I don't know. I guess it's coming in. See, you're talking about an atom that's way out there, outside of everything.
No,
A
it's on
lonely
the edge.
atom.
It's on the edge.
Yeah, but as soon as it comes in, it's got someone up behind it.
Why?
Well, because it's on the edge. But what is the edge? The edge is a whole bunch of atoms.
Yeah.
Actually,
Those, for example.
I have a better explanation for that in the book, and that's that the edge of the universe is woven, is scanned by threads.
Yeah, it's magnetism.
Yes, magnetism.
But
That's on the edge of the
Yeah, I'm not
universe.
talking about that one.
But see, when you come in from these thwarting threads, you do have threads behind you. So you're reconstructing the rope, but you're something you're releasing behind. It's not like you're not. You're not pulling everything behind you, especially if you're just one atom that's coming in.
Mm-hmm.
You've left some atom behind to the side of you and then farther behind.
Yeah, but there's more atoms towards where you're
Yeah.
relocating.
Yeah, but the other guys are pulling.
Are you
You're
eating more rope than you're dispelling? Because there's more behind you? I guess that's the question.
well, assuming that were the case, the question there would be maybe if the magnetic field increases. I don't know. I'd have to think about that. That's a good question.
Next question.
So I'll take that as an action item, as homework.
We talk about prime movers and things that move on their own, right?
Yeah, yesterday.
Yeah, we talked about that yesterday.
Yeah.
Something that moves on its own as opposed to something that gets moved upon.
Right.
Or it reacts to.
Right.
You say that atoms pulsate or pump, essentially grow and shrink repeatedly. Is
Yeah.
this self-propelled or reactive? In other words, is the atom doing the moving or is the atom being pumped?
That's a good question, because if every atom in the universe is doing this, the question is if the other atoms are inciting our atom, our target atom, right? We have a test atom, right? And there is an influence. For example, if the sun has an atom that is pumping faster because suddenly it got squashed and releases thread, and we have higher frequency, and now that frequency travels all the way, that higher frequency, the shorter wavelength, right, link lengths, travel to this atom, and now this one begins to pump faster, then there's been an influence from one atom to the other. Okay? So in that sense, atoms do influence other atoms. But the question here is, again, we're talking about the origin of motion. Did anyone set this in motion? In other words, was there a moment where, which I explained yesterday, and I do explain that also in the book, where I'm saying God has a frozen universe, he's got, everything just static. And now suddenly, how does he create motion for the first time? Well, all he's got to do to create motion is to move one atom in one direction, and all the other atoms in the universe adjust their location with respect to it. So all you got to do to move the entire universe is to move one atom. If I want to move God right now, it's very easy. I just move my hand like that, and God is changing his distance with respect to my hand. And he can't avoid it. You know, this is a power that I have over God. I change the distance whether he likes it or not. And by moving my hand, I'm moving God.
No, because he lives in your hand, bro. You can't get away from him.
But that's the point. The point is that motion, all you need to do is move one atom in the entire universe.
What's
You
that
move
have
everything
to-
with respect to it.
But what's that have to do with the pulsating atoms?
Well, in the sense that, again, if we start from scratch, where we say, let's start with no motion in the universe, everything is frozen, right? How to create motion for the first time in one atom? Well, all it's got to do is move with respect to all the others. That's all we would need, right? That would be the scenario. And I don't think that's ever happened. I think the famous universe, as we call it, all the matter in the universe was always in motion. There was no point where someone kick-started it. And we have trouble with that because we always have this idea that there's been an origin, a starting point. And there was no starting point to the universe, to the matter in the universe. Because again, the word universe means matter in space. And space is not a medium like water or like air. Space is nothing. There is no such thing as space. All we have is matter just floating with respect to each other. Every atom with respect to each other. And I think that never did one of those atoms stand still with respect to the rest of matter in the universe. It's always constantly in motion. There was no origin to motion. So to say, did an atom start moving? No, we can't say that. All we can say is that, yes, when one atom vibrates at a higher frequency, it does influence the next atom. There is that kind of influence, mutual influence from atom to atom. We do have that. So there is an influence. Now, can this one influence the other one? Also, if you can get this atom to vibrate faster, it's got to influence the other guy. And in fact, you can do the opposite, which is what they do in some of these labs. They try to freeze. They try to reduce the frequency of an atom so it doesn't vibrate as much, and that's what we call cold, because vibration is hot and less vibration is cold. And they try to get it to close to 0 degrees Kelvin, which is, 273 degrees below zero centigrade. And that's as cold as it gets. But they never got there. They got close to, I think, to 3 degrees Kelvin. And I think that's what they've managed to achieve. How they measured that, I'm not sure. But they got it to very cold, which means that that atom is barely moving. And the wavelength's got to be very long. But then how do you, if you put a fire underneath that, what are we saying? We're saying that you're imbuing motion to that atom. Now it's vibrating at higher frequency. The rope, it releases that rope, or the vibration of that rope causes the rope to have shorter lengths, and you have higher frequency, and now you have that atom at higher temperature. If you could measure that one atom, you would have a higher temperature.
So is it safe to say that the atoms aren't pulsating? It's more like, they are pulsating, but they aren't doing the pulsating. They're being pulsated by other atoms, like in a really long game of telephone.
It's a two-way street. They are pulsating and they are influenced in their pulsating, because you can modify by just take water and heat it, till it boils. What have you done? Well, you've sent higher frequency to that atom, and now it's vibrating at a higher velocity or frequency, and so now, that's why it boils. That's why water boils. And so you have influenced that atom. We can't influence atoms. Now, the atom still moves on its own, but other atoms can influence that atom by making it, move at a faster rate. So I think we have both situations. So it's a tricky question, because here we have one of those little dualities, but it's a rational duality in this case. The atom moves and the atom is moved. It's a mover and moved at the same time. It moves and it influences the atom next to it. So both things are happening. So when we have Mr. Aristotle. In fact, the Stoics already used that. They said the Stoics defined also motion, not motion. They were defining existence, the word exist, and they said, what does exist mean? And they said, well, it's very simple. That which can move something else, and that which is allowed to be moved. In other words, what exists is that which can move because it's been moved by something, or which can move something else. That's what they called existence. That's what they referred to when they said exist. And that's essentially your question. You're saying, does an atom, have motion, or is it influenced by motion? The question and the answer is both. It does have motion, and at the same time, it can influence motion, be influenced by motion. It's got both. Okay, and in that sense, we can say it's a duality, but it's a rational one. Unlike the wave packet, that's an irrational duality.
You were talking earlier about heat. Just to clarify, is heat, when you heat something up, is it the atoms that are vibrating, or are you changing something with the rope frequency?
You're doing both. Remember, all this is one system. The whole universe is one system. Some stars are far away and we don't consider them, but really it's all one system. What we have is, and we take the basic system, which is two atoms bound by an electromagnetic rope. Okay, and so when an atom, typically, let's say we come to an atom or to a pair of atoms, we just see them pumping, boom, 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 boom. And the rope, well, they could do it alternatively. I'm not sure about that. I've considered both scenarios. Where they pump alternatively or when they pump simultaneously. But the point here is that I'm trying to make is the following: you come to two atoms. You have God's eyes. You can see these two atoms, right? So they're pumping, and the rope is sending the torsion back and forth, along the rope in both directions. Now, what happens? Somehow you stimulate one of them. So this one begins to pump faster or vibrate fast because there's several motions to an atom. There's vibration, there's pumping. And so now what happens? That doesn't go unnoticed by the rope. The rope, now if this goes faster, what's it doing? It's making the rope torque at a faster rate.
Wait, but there's a difference when you're talking about the atom vibrating, moving back and forth in a 90-degree parallel. That's not that you're not adding to the rope. Well, if it's pumping faster, then you are.
Both, I think. All vibration motion, I think. This is the way I visualize this. All vibration motion of an atom, whether it's shaking, whether it's pumping, anything that you can imagine, or up and down, I think all of them affect the rope in one sense. In other words, if you were to stimulate, if you had God's eyes and you were able to stimulate one of the atoms just to go up and down, or back and forth, or pump, I think all of them would have an effect on the rope. And the effect would be, because it's vibrating at a higher frequency or higher rate, I think that shows up in the rope as higher frequency. In other words, the rope now, what I mean by that is the links will be shorter because it suddenly gets the stimulus. And so the rope is torquing at a certain rate, and suddenly you give it a whack, and now it's going, it's moving faster. And that faster, since light always travels at the same speed, it has to be a trade-off between frequency and wavelength. And what I'm saying is the wavelength gets shorter and you have more links, right? That's what I'm saying. At a higher frequency, at a higher temperature, or any way you want to look at it, depending what you're analyzing. So that's the sense that that's how I'm visualizing this whole thing.
What part of motion do you think someone could get tripped up or misunderstand? Like, what part do you think you would have to clarify the most, or what part have you clarified the most often?
The definition. The definition, because people have, again, they use the synonym, the word change. That's used constantly, and that's where we're at today. And people are not aware of the history of the word motion, of what has happened throughout time. And it turns out that, throughout the centuries, they've all defined it in the same way. They defined it with synonyms. And so we did not have a definition. We still don't have a definition officially out there. We're proposing the first definition, scientific definition of what motion really is. And so when you encounter someone, he talks about motion. Since it's the fourth word on the list here, you can see, fortunately I still have it up there.
That should always be up there.
It's a key word. It's a key word, and you can't do without it in physics. And people take it, oh yeah, motion. We know what motion is, like Newton said, no, we don't. So we need to clarify it's two or more locations. And that's where I see the big problem with the majority of people who encountered this definition for the first time. There's a clash of cultures. And
that
obviously,
seems to be a recurring theme with this new language.
yeah, remember this language is a problem because people are not used to the language, and they want to bring the language of ordinary speech into the discussion, and you can't allow that to happen. And so this is where we run into trouble. People are not used to the language, and when you say something, they're understanding something very differently, or they don't pay attention to the wording because they're not conscious. Like, whenever someone talks about object, motion, exist, I get nervous. I get on all fours and start getting nervous. And people don't have that reaction because for them, these words are not important. We have Dan.
One last question from Dan.
Okay.
Could an atom be thought of as a convergence of slack ropes so they become threads because the rope is always taut?
They become threads, like loose threads? You mean like swinging threads? Is that what you're saying? Swinging threads, that's not an atom, that's magnetic field. So if we're talking about threads and you're talking about like the slack of extra threads out there, the only way I can see threads again is always a function of spinning. I think that always when you see a thread and we talk about the thread, we're talking about spinning. And that immediately takes it to the magnetic field context. Whereas the rope is always straight. That's why some people say, your rope theory, or they said, yeah, the rope swings around, or blah. No. The thread is different than the rope, and the thread, whenever we have a swinging threads, we're talking about a magnetic field. Whenever we have a rope, it's always straight.
I definitely want to talk about atoms.
Just a little bit loose.
Just a little.
Well, how loose is a little bit?
Well, I definitely want to talk about atoms next time. Your atoms. Because there's a lot of mysteries in the atom, the Gaede atom.
Okay, tomorrow we deal with atoms. If you have questions on motion, because maybe we haven't exhausted all the issues here, I just want to maybe recap real quickly. Motion cannot be continuous. It's got to be incessant. We got to use an adverb. Incessant is an adverb for the purposes of physics, so it's incessant, perpetual, eternal. You can use any word of that nature and it's going to be considered an adverb because an adverb is what qualifies a verb. On the other hand, an adjective such as continuous only can be applied to an object, okay, in science, in physics. The other one is that all these definitions, as you can see still on the board, have to be comprehensive. In fact, some people think that they can go in there and say, well, I like your definition of location, but I don't like your definition of motion. No, you can't do that. This is all comprehensive. In other words, all these definitions are tied into one another, and you can't shake one of them and not believe that you can get away with shaking it because you're shaking the foundations.
Well, doesn't it depend on which one you shake?
Well, if you have a better definition,
my point is you can't be okay with motion and not be okay with location because motion builds on location. But the other way around, you can be okay with location, but not be okay with motion.
Maybe, because again, it depends on which words you're going to use to define. Like, and we have more words there that come later, like exist and what is straight, what is a dimension, and so on. There's a series of words that we must define in physics in order to talk intelligently. And my only point is that you got to be careful with shaking some of these words. What is a concept? A lot of these things, people say, well, I don't like your definition here. I'm going to use this other definition, but all the rest I'll accept. Not always can you do that. You got to be careful because it's like having this structure of toothpicks or matches, and you pull one matchstick out and the whole structure falls. And that's exactly what happens here. So you got to be careful when you twiddle around with these definitions. I'm not saying you got to memorize them. Maybe you can improve on them, in fact. But the point is, these definitions, you got to be very, very careful because they form the foundations of physics, okay? And so it's a comprehensive system, one. The other one, you can't use adjectives for motion. And the third one is, well, as my son challenged me. He thinks that maybe we need time to define motion, and I'll just have to beat him up after class today. And
Well, I guess that's the point, to be able to question the definitions instead of having to swallow them whole.
no, right, and that's what we're here for.
But I definitely want to talk about this question tomorrow.
Okay.
The fact that an atom could be thought of as a convergence of slack ropes.
Atoms,
Because essentially you're saying if all ropes are taut, that means any slack goes into atoms.
Any slack goes into yeah. Or well, it also, remember, the slack also is absorbed by the rope. The rope can absorb slack in the form of amplitude, and it also in the speed in which it torques. In other words, the frequency in the wave, in our case, the link length, and so on down the line. So, anyways, we'll continue tomorrow, and I hope that clarified some points that were not clear yesterday. We'll see you tomorrow. Bye bye.